microphone now working?
Okay, can you repeat that again? We couldn't hear you.
Is my microphone and everything now working?
Okay, now I think it's better.
Yeah?
Yeah.
Okay. Right. So let's go. Are we good?
Yes, we can start. Euron, we can start also on Facebook.
Yes.
Okay. Perfect. Right. So, hello everyone. This is my first attempt at doing a talk or a lecture live stream. So do bear with me. Depending on how things go, I've set up my usual YouTube setup with my camera and microphone and everything. So hopefully the picture and the sound is all okay. So I am Dr. Tom Crawford. I'm a mathematician at the University of Oxford in the UK, and I've been asked to talk to you all today about the math and to try and make it particularly topical and relevant to the current situation across the world. We're going to talk about math in the context of epidemics, and perhaps touch a little bit on how we can use math to try and understand what's happening with COVID-19. aka coronavirus. But before I get to the actual math, I've been asked to introduce myself a little bit. So I thought the easiest way to do this is to tell you a little bit about me. So as I mentioned, I currently do math at the University of Oxford. So I teach first and second year undergraduate students. I originally grew up in Manchester, which is in the northern part of the UK. You've maybe heard of some of the football teams. They tend to have two good football teams. I'm Man United rather than Man City. And so I grew up in Manchester, and then I came down to Oxford to study maths for my degree. So I spent 4 years here doing that. Then I went over to Cambridge to do my PhD in applied maths, and I was studying fluid dynamics. So I was looking at trying to answer the problem of ocean pollution. So the big question we were interested in is when river water enters the ocean, can we mathematically model that and then use that knowledge and those equations to be able to predict and then track how river water moves through the ocean, with the idea being that the river water will contain all the pollution from the land. That was my project. I worked on for 4 years. I then had let's call it a real job, working for the BBC as a science journalist. So I helped make a science radio program for a year, which is how I got interested in communication and public engagement work and sort of discussing science and math with everybody. And then that led to the formation of Tom Math, which is what I do now. So I have a YouTube channel and website called up there in the corner of the board that never gets rubbed off, where I make videos talking about different mathematical topics. And as well as that, I then now teach back here at the University of Oxford. So that is a whistle-stop tour of me and how I got to where I am. So now we're going to start by basically doing some maths and talking about disease spread and epidemics. So there's going to be sort of two parts to the talk. So we're going to start off by first of all looking at exponential growth. So this is something that's been talked about a lot recently with disease modeling. So talk about exponential growth. So the first question sort of asked is, well, what is exponential growth? What does exponential growth actually mean? And so in the context of a disease, it's to do with the rate of spread or the growth of the number of cases of people that are infected. So I think that to get a feel for what it is, it's better to do an example. So if you start off with a single person, okay, so let's start off with a single person who has the disease. And now This person is going to spread the disease because they are infectious. So let's suppose, let's suppose they're doing this by accident. They don't realize they have the disease, which is of course very relevant with coronavirus. And then given the current estimates that we have for coronavirus, one person with the disease, on average, is expected to pass the disease on to 3 other people. So our one person is going to infect 3 others.
Tom,
yeah.
Let me interrupt you. I think some students are having difficulties listening to you. I believe they cannot hear. They're saying that the sound quality is not very good. Can we maybe try something about that?
Okay.
No, I think just if you can just the laptop, bring it a bit closer to you, because I think because of the distance it might be.
I have a microphone which should be pointed at me, which is recording. Is that any better, or is that still? Let me just check it's still recording correctly then. Right. Okay, is that better now?
I can
hear. For some reason it had changed and was recording my sound completely wrong. Hopefully this is better.
It's the same, but I can hear you. For example, for me there is no issue, but maybe maybe everybody should just the volume, increase your volume, I think.
Let me just check. Oh no, I'll tell you what it is. Okay, how about that? Is that clearer, better?
Yeah, this is way better. Yeah.
Okay, fine. It's silly. Google Meet had changed my default settings. Okay, good. Sorry about that, everybody. Right, so I will carry on talking about the exponential growth idea for disease spread. So we have one person who, for a disease like coronavirus, is going to infect 3 others on average. This is sort of the data we have at the moment. Now, the reason the growth is exponential is this idea that these 3 people will now go on, and each of those will infect another 3. So I'm going to get another 1, 2, 3, 1, 2, 3. Really testing out my artistic talents here. 3. Okay. So we've gone from 1 to 3 to 9. And then the same pattern is going to repeat and going to happen again. So we're then going to go, each one of these 9 people is going to infect another 3 people. So basically what's happening at each step is we're multiplying our previous number by 3. So this is what we mean by exponential growth. Rather than adding on a consistent number of people, what we're doing is we're actually multiplying the previous number by this consistent ratio. So here the growth rate being 3. And so this is going to continue. So we get 27, then we get 81, and it carries on. So if you were to draw a graph of this function, for example, so I'm going to rub off my stickman drawings. So what this might look like, I will attempt to do it to scale. So this is time, and this is going to be sort of people, number of people with the disease. So at the beginning, we've got just one person, so we're kind of here. Then we've gone up to 3 people, still quite small. Then we got up to 9, so that's going to kind of be here. Then we've gone up to 27, so that's like at the top of the board. So very, very quickly, this is growing. And this is sort of potentially looks like one of these graphs that you've maybe heard a lot about or seen a lot about that are described as this exponential growth curve. So
The reason exponential growth is sort of a worry is that it's one of the fastest rates of growth that you can have for a particular function. So well, actually, before we do that, so if we were to try and think of a formula for what we've got here and what's happening, then if we take, so let's call this one is going to be the 0 case. Okay, so if we call this n equals 0, right at the very, very beginning, and then after one sort of time period, so that would be the period of being infectious with your disease. So let's just call it 1 week to make things easy. So after 1 week, we are now at n equals 1, where n is the number of weeks. Then after 2 weeks, we have 9. This is n equals 3, n equals 4, and that will carry on and increase. So the formula here, what we've got is it's going to be 3 to the power n. So again, this is representing our exponential growth, where n is the number of weeks, and we have this n up here as our power, or as our exponent. So n here is the exponent. And this is why it's called exponential growth, because the variable, the number that's allowed to change, which here is n, which is our time or our number of weeks, the number which can change is in the exponent, and so that's telling you that it's exponential growth. And the reason this is worrying, the reason this is bad, is this is always going to beat what sort of the other type of growth that gets discussed in these situations, which is polynomial growth. So as an example, here we've got 3 to the power n. So what we might have for a polynomial rate of growth would be something like, let's say it was n cubed, just to use the same number as we had before. So something like n cubed versus 3 to the n. Both of these are functions that grow as n increases, but this one is going to grow much faster than this one. And we can compare them by calculating a few values for, or a few of the sort of outcome for different values of n. So let's do that. Actually, I can probably just fit it here. So if we have our two functions, so we've got 3 to the n, and we've got n cubed. Okay. And then we want the value of n equals 0, n equals 1, 2, 3, n equals 4, etc. So if we compute the first few terms we have here, for n equals 0, 3 to the power 0, that gives us 1, and 0 cubed is 0. Okay? When n is 1, this is 3, and this is 1. This one is going to be 3 squared is 9, 2 cubed, 2 times 2 times 2 is 8. Cubed is 27. This is now also 27. So this is quite interesting. So we can see here the exponential one is bigger, bigger, bigger. Now they're kind of the same. Well, they are the same. But then the next one will go back to this one being bigger, because this will go to 81. And this one will be 64. Because this is 4 times 4 times 4. And this is 3 times 3 times 3 times 3. So, and this will carry on. And you'll see that this one will always be larger than n cubed. So if we were to put them on a graph together, what you would see, take that one off. So you would have your 3 to the n curve would look something like this. And then your polynomial, let's use a different color, is going to come through 0. And what we've got here is this interesting idea of them being the same when n is equal to 3. So that means these two have to perfectly touch. So you have a tangent between your curves. So the two curves have the same gradient or the same slope. So this one's going to come in and just beautifully touch there, but then stay underneath. So this would be when n equals 3. But as you can see, what's going to happen if we carry this on in the future is this one will go up like so, but the yellow one, the exponential curve, is going up much faster. So whatever point in the future we go to, like say here, you go up and you see the exponential one, the yellow one, is always above the purple polynomial curve. So this was just for n cubed, which is quite a small polynomial. But even if we did this for a larger value, you would still get the same kind of behavior. Eventually, it would just take longer to happen. So for another example that I have already calculated the numbers for is, let me just check. So the next one, perhaps, would be n to the 4th. So we've looked at n cubed. So now if I look at the number to the power 4, and then we want to plug in these values and complete the table just like we did before. So n to the power 4, this is still 0. 1 to the power 4 is 1. 2 to the power 4 is 16. So we can see now this one is bigger than the exponential at this point. N to the power 3, this will give us 81. Then we're going to get, testing my arithmetic, 64 times 4 is 256. So this one is much, much bigger at the moment. We're at our 4th week in, and here we've got 256 for the polynomial, n to the power 4, and we've only got 81 for the exponential. But if you carry this on, which, as I said, I did earlier, we go down to n equals 7, down here, this value is equal to 2,400. Wait a minute. Yeah, 240. Not that one. The n to the 4th is 2,401, and the other value is 2,187. So this one is still bigger. We still have the larger number for the polynomial, but it's getting close now. And the next term, we're going to see the exponential actually will win. So when n equals 8, the exponential goes up to 6561, because it's 3 times that one. And this one is now 8 to the power 4, which is 4,096. So now the exponential one wins when you get to n equals 8. So as you increase the power in your polynomial, so over here, so we just looked at n to the power 4. So as you make this power larger and larger, it takes longer for the exponential function to be bigger than the polynomial, but it will always happen. You can keep going forever and ever and ever, and eventually the exponential will always be bigger. And this is why exponential growth is an issue, because it just continues to grow forever, and it will always grow faster than any polynomial that you can write down. Okay, so the final thing we can do is, and this is quite a fun question, is you can ask, when will the exponential beat the polynomial? So I just clear the board. Right, so if we now say we have our exponential growth here, 3 to the n, so this is the exponential. And then the polynomial one is going to be n to some power k. So we just did 2 examples where k was 3 and where k was 4. So when k was 3, we found that the exponential was always bigger. So x was greater than polynomial always. And when k was equal to 4, it worked when n was equal to 8. That was what we saw in our table when the exponential became bigger than the polynomial. Now, if we want to consider this for a general k, what we need, we have an inequality that we can try to solve. So we have, we want 3 to the power n to be bigger than n to the k. Now, k is fixed. So the idea here is that somebody has given you k. So, you know, you've just gone out and asked some random person and said, you know, maybe I'm asking you all currently watching, pick a large value of k to be the degree of our polynomial, so to be the term in our polynomial. So k is fixed, but what we want to do is figure out what value of n makes this one bigger than this for this particular k that we've been given. So the way to do this is we need to rearrange to get an equation that tells us what n must be bigger than, basically. So the problem is we have an n up here in the power. So it's not quite as simple as just rearranging the equation. We have to use, basically, we have to use logarithms or logs. So at the moment, we have something to a power, and to change it into something that's not in a power, you use the function called the log. So don't worry, you've not heard of a log, but they're pretty powerful functions. They're kind of the opposite, taking something to a power. So if we now take the, let's just think about this. To the base n of both sides of our equation, that needs to be greater than log to the base n, n to the k. But now, so all I've done is taken the logs of both sides. But now the idea is taking something to the base n in your log, when that is the same number to a power, that just gives you the power. So what we've done by taking the log is to turn this term into just something involving k. So now we've done that, we can rearrange this and say what we need to do is just, if somebody gives you a k, you just have to pick n so that log base n 3 to the n is bigger than k. And if you can now play around with this formula here for our examples that we did above. And I was playing around with this earlier. So when k equals 4, for example, our formula tells us we need to find an n and then plug it into our calculator. So, you know, you just try by guessing, basically. So if you started and tried, let's say n equals 7, you do log base 7 of 3 to the power 7, and you calculate what that is. And when I did that, I got, I didn't do it for 7, I did it for 6. Okay, so when you do it for n equals 6, you get 3.68. So when n is 6, this gives you 3.68. But k, remember, is 4. So that tells you that n being 6 is not quite big enough for the exponential function to win. And we already knew that because in our table, we showed that the exponential wins when n is equal to 8. So if you then plug in n equals 7, you get 3.9 something. But when you plug in n equals 8, you get 4.15, I think, which is bigger than 4. And that tells you that your exponential function will win, be bigger than your polynomial after 8 weeks. So when n is equal to 8. OK, so we'll leave it there on exponential growth. That's just sort of a bit of a whistle-stop tour on what exponential growth is, some interesting things you can do with it. And as I said, I think if you pick some values of k, it is quite fun to plug these numbers into your calculator and try and see at which point the exponential will beat this particular polynomial power. Because it will happen eventually, definitely. Can confirm this. For any k, you will eventually find an n large enough such that the exponential always wins. Right, so now I want to talk about the SIR model. So this is basically how you model the spread of a disease. So the key idea here is just to try and give you all a bit of a feel for how you use maths to understand the spread of a disease and how it can be helpful, you know, in situations like that we're sort of currently seeing. So the model I'm going to talk through and explain is a very, very basic model. So I just want to emphasize this is the simplest disease model that you can create, really. And obviously the ones currently being used by the actual scientists trying to understand and model COVID-19 are using much, much more complicated models that require to be computers to solve them and various other things. So this is, whilst this is the starting point for a disease model, it is way simpler than the actual models, you know, that we are currently using. But hopefully by talking you through the simplest case, you can at least get an idea for how these models work. That's the idea. So the model, as I said, is called the SIR model, which again, you may have heard, if you've been looking into the maths behind disease spread, you may have heard about this or seen things about this. So the idea is to take your population. So let's suppose this is our population of our particular country or even of the world. So this is the whole population, this circle. Now, when there is a disease epidemic or an outbreak of a disease, there are three possible situations that a person can be in. So the first one is maybe you have the disease. So let's suppose this proportion of the people have the disease. We label this I, and I here stands for infectives. So infectives meaning these are people who are infected with the disease at the moment. Now, there will be some people who have not yet caught the disease, so people who do not have the disease. So maybe that's this portion, slightly larger, which we call S. So S here is going to be for the susceptibles. So these are people who are susceptible, meaning they could possibly catch the disease. And then the final category up here is going to be R, because if you have never had the disease, you're in S. If you have the disease right now, you are in section I. And the other possibility is maybe you had the disease and then you recovered from the disease. And when we say recovered, for the purposes of our model, so this is R for recovered, but for the purposes of our model, this also includes people that may have died from the disease. So even though somebody dying from a disease definitely does not mean they have recovered, for our model, we just put it in the same category. So it just means somebody who's had the disease and is no longer infectious. So once you've moved, so you start in S, you move to I, and then you move to R. So SIR. You move in that order, and you finish off in a recovered section. Now, so this is the sort of the simple setup. You have these three parts of your population. And then what we want to understand is how the numbers in each population, how those numbers are going to change over time. So how they're going to change as the disease sort of spreads. So like we were doing with our exponential growth, we want to start with some initial numbers, some values, and see what happens over time. So what that means is we actually want to know the change of these variables. So I'll leave up the SIR definitions there. So what we want to know is how do these numbers, how do they change? So if we want to talk about a rate of change, then what we do is we calculate some derivatives. So again, if you've never heard of or never studied derivatives, don't worry, you can really understand exactly. It's just what are we representing the change in a particular value over time in this particular case. So for example, the change in susceptibles, right, as ds by dt. So the d on the top basically means change. So this is saying, how does s change, where s is the number of susceptibles? How does s change over time? Because we have the t on the bottom. So this is saying, how does the number of people susceptible to the disease change as time passes? So that's going to be the sort of the starting point for the equation about S. And then we want to know the same thing about the number of infected people and the number of people that recover. So we also want to know, how does the number of infectives, so you do DI, we want to know how that changes over time. And then we want to know about the number of recovered, dr by dt as well. So we've got three things that we want to know and we want to be able to calculate. Now, to be able to make progress, with any mathematical model, you have to start to make assumptions. So we could try and simulate the real world exactly as it is. But then, you would require like the world's biggest supercomputer, and you'd have to run the simulation for hundreds of years. And so like, it's just not feasible to sort of model the real world. Like you basically have to create an exact copy of our current world and to create such a complicated simulation. So what you do when you're doing a mathematical model is you try to understand, or you try to make simplifications to just pick out the really key important pieces of information. So a simple example I like to mention in these situations would be, if we were trying to, let's say we were trying to model how fast Usain Bolt can run the 100 meters, then lots and lots of things will affect how fast he can run the 100 meters. Maybe what he had for breakfast might affect how fast he runs that day. Maybe what he watched on television a week ago might affect it. But given those two options, I would say it's probably more likely that what he ate that morning will affect how he performs rather than what he watched on television 1 week ago. You can't say that the television doesn't have any effect, because maybe he watched a very inspirational documentary that motivated him and made him train extra hard that week. So you can't really say it won't have any effect, but I think you can certainly say it will have less of an effect than his last meal that he ate before the race, for example, which knowing Usain was probably chicken nuggets. So that's like, it's a sort of exaggerated example, but if you were going to do a model and you only wanted to pick one of those variables to put in the model, you would obviously pick the food one rather than what he's been watching, because it has more of an effect. So what we want to do here is, rather than modeling everything in the world, so for example, the weather will have an effect on the spread of the disease is one example, but it's probably not as big of an effect as for example, the contact between people. So given that we want to make this as simple as possible to have a chance of solving it quickly and have a chance of understanding what's happening, we're going to choose to model contact between people instead of the weather. So the weather does have an effect, and that would come in a more complicated model. But for our simple model here, we want to just focus on the most important aspects of the disease. So that leads us to the situation where we need to make some assumptions. So assumptions are sort of rules that we follow to simplify the real world. So for our disease, for the S, particular assumptions. So the first assumption that we make is going to be, I'll write these over here. So our first assumption is going to be that the population is going to remain constant. So the total population doesn't change. So the circle population doesn't change. So the circle that I drew on the board earlier, that I said represented the whole population, So that size of that circle doesn't change, because if people happen to die from the disease, they went into the category R, and so so deaths from the disease were included. But what we're excluding here are natural deaths, so people dying from other reasons that are not this particular disease, and we're excluding natural births. So we're saying that for the simplification of our model and to make things easier, we're going to ignore birth rate and death rate for this population. So that's the first assumption. Then the second assumption we're going to make is about how the disease is transmitted. So we're going to say that the transmission of the disease, the way it is passed from one person to another, is going to be, transmission is proportional to the number of contacts between the infected people I and the susceptibles S. So the transmission of the disease is proportional to the number of contacts between I and S. So this is saying you have somebody with the disease, which is a person in the I category, and the only way that a susceptible can get the disease is by coming into contact with somebody that already has it. So this is true for a lot of diseases, okay? It's an example where it's not true might be something like malaria, which is spread through mosquitoes. So that would require modeling, people and mosquitoes. But with something like COVID-19, coronavirus, this is spread, we know this is spread by people sneezing or coughing, etc., and contact between, or close contact, close proximity between someone who's infected and someone who can catch the disease, someone who is susceptible. So it's going to be assumption number 2. And then the third and final assumption is going to be that when people have the disease, so the infectives are going to recover at a constant rate. So again, this may vary per person. So for some people, recovery might take longer due to health conditions or due to their level of fitness, different issues. But that, for our purposes, is not that much of an important consideration. If we just say, the very simplest thing we can do is say, after everybody catches the disease, they then recover after a week or something of that sort of level. So that's to do with what we talked about for the exponential growth again, where we said that someone was infectious for about 1 week. So that's sort of being built into assumption number 3. So now we've got our assumptions, what we can do is try and build our equations and build our model. So the most important one here actually is going to be number 2. I'm going to do it in pink. So number 2 says that the disease is transmitted, that rate of transmission is going to be proportional to the number of contacts between somebody who has the disease, so they're infectious, somebody in I, and somebody in S, somebody who's susceptible and doesn't yet have the disease. So what that means is that the change in our population of susceptibles, that is going to decrease when somebody moves from S to I to R. So S can go down when somebody becomes infected. So this is telling us that there's a minus because S is going to decrease, because this is the change in S. So the change in S will be negative, it will only go down. And it's going to, by assumption 2, it's going to have some rate of transmission R, and then it's going to be I multiplied by S. So just to recap why that is the case. So it's negative because S has to decrease. People leave category S and go into category I. So S is decreasing, which gives us this negative sign. And as it decreases, we have a rate of transmission. So R here is the rate of transmission. And And we've said this is a constant by assumption 2. So that's the rate of transmission. And then we've got I times S, because again, in assumption number 2, we've said that for the disease to be transmitted, an infective I and a susceptible S have to come together. So the rate of transmission depends on the number of I and the number of S and when they come together. So that's why you need to have both I and S in here. So as a simple example, if I was 1 and S was 1,000,000, then you can straight away see that this will be a reasonably small number, whereas if I was 900,000 and S was 1,000,000, this would be massive. So in the first case, there aren't very many transmissions. There's only 1 infected person. But in the second case, there will be a lot more. So you need to have both I and S in this equation. So assumption 2 just gives us this term. And that's the only term we're going to get for the way in which the susceptibles S can change. Because the only way, sort of the route that you can take is to go from S to I. So people who have now left S at this rate must arrive in I at the same rate. Because as you move from being susceptible to catching the disease, you move from S into I. So the I by D has a plus RIS here from assumption 2. Now, this is where assumption 3 is going to come in. I will do in blue, because assumption 3 tells us that if you have the disease, you can then move, like over here, you can move into category 3 and you can become recovered category R. And this is going to happen also at a constant rate. So that rate is going to be the constant A. So A is the rate of recovery. Rate of recovery, which goes there. And that's going to be multiplied by the number of infectives that we have. Because if you're going to recover from the disease, you have to have it in the first place. So it's going to depend on the number of people that have the disease. And then, like before, if you've moved from I, you've then gone into S. So there's the minus here, which means you get the plus AI here. And that is now our full model. The assumption 1 about the population not changing, so that just means that we've ignored in the susceptibles that we have births and deaths. So we could, for example, add in extra terms into the first equation for people being born and people dying from a different cause. But the reason S is just this is where assumption 1 comes into the model. So now, to finish off, what we've got is a set of 3 equations. So I'm just going to, let's rub off the assumptions now. And what we want to do is try and solve these equations to work out what S, I, and R will look like and how they will change over time. Now, unfortunately, we can't solve these directly because this is an equation for S, but it depends on I. This is an equation for I, depends on I and S, and then this depends on. So they all kind of depend on each other. So there's no easy way to solve them. So you basically have to put this through a computer to be able to solve what's happening. And what you see is the following graph. And this, again, is going to hopefully be similar to something that maybe you've seen before, or seen online if you've been looking into the modeling of this pandemic. So we have time down here. We have population up here, number. And then what we've got are these sets of equations. So we want to draw S, I, and R. So I will do S in yellow. So what happens to the susceptibles is you start off with lots of people up here. So lots of people are able to catch the disease at the very beginning. And this is especially true with COVID-19 because it's a new disease. So nobody has immunity because it's never been seen before. So almost everybody can catch it at the very beginning. And then as the disease progresses, more and more people catch it. So S will start to decrease. And what you see is something that looks like that. through time. So you start with everybody being susceptible, and by the end, not many people are susceptible. Now for the, so that's S in yellow. Now for I, the number of infectives. Now this will start off quite small. So at first, not that many people will have the disease. And then as time progresses, so it starts off down here, and as time progresses, this will grow as people from S become infected, which we sort of said here, this term. So this one starts to grow, and then eventually will come down as well. So that's going to be I. And then finally, the recovered, the people who've had the disease. So at the very beginning, nobody has recovered right at the very start, because they either can catch it or already have it. And then as people start to, they move from S to I, and then after I, they then move into R. So this one is going to start off quite small and then increase and go something like that. And that's going to be R. So what you're seeing is the number of people who can catch the disease is very high at the beginning, and then as people catch the disease, this decreases towards 0 over time. The number of people that have recovered from the disease is 0 at the beginning, and then that starts to increase as more and more people catch it. And in the middle, you start with not many people have it. Then there's a peak when most people catch it, and then you start to see this drop off. So there's been lots of discussion in the news about saying, you know, we need to get past this peak, and the peak that people are talking about is this bit here. So there would be some time here, which would be the time of the peak. And so once you get past that, you start to see the number of infections go down, and that's good news. And that's what governments and countries around the world, I guess everybody around the world is really hoping we're going to see as soon as possible with COVID-19. Okay, so I think I'll leave it there. It's about 45 minutes. So I talked about exponential growth at first, and then talked about the SIR model. So now I think I will answer people's questions. So let me just get a drink of water because I'm quite parched. Okay, right.
Thank you very much, Tom. It was a very thorough presentation. It was very fun listening to you.
You're welcome. Okay. Okay, right. So questions. Okay, right. What we got? We've got. Okay, Leonita has said, is there a reason why we are comparing 3 to the n and n cubed? No, there is not a reason. So, leave that. I'll leave that stuff up. So I just gave the example.